Welcome to our comprehensive guide on angle modulation, a fundamental concept in modern communication systems. In this video, we'll explore the principles behind frequency and phase modulation, their mathematical foundations, and practical applications. Angle modulation plays a crucial role in transmitting information efficiently and reliably, especially in radio broadcasting and wireless communications. By the end of this journey, you'll have a solid understanding of how angle modulation works, the differences between its types, and why it's so widely used. Let's begin by defining what angle modulation actually means and why it's important in the world of signal processing. Angle modulation refers to a technique where the angle of a carrier wave is varied in accordance with the message signal. Unlike amplitude modulation, which changes the amplitude, angle modulation changes either the frequency or the phase of the carrier. This approach provides better noise immunity and is widely used in high-fidelity audio transmissions. Angle modulation is divided into two main types: frequency modulation FM and phase modulation P. Both have unique characteristics and applications which we'll explore in detail throughout this video. Understanding angle modulation is essential for grasping how modern communication systems maintain clarity and reliability. Frequency modulation, or FM, is a form of angle modulation where the frequency of the carrier wave is varied in proportion to the amplitude of the input signal. This means that as the message signal changes, the frequency of the carrier shifts accordingly. FM is renowned for its robustness against noise and interference, making it the preferred choice for radio broadcasting and two-way radio communications. The clarity and fidelity of FM transmissions are superior to amplitude modulation, especially in environments with significant electrical noise. Let's now look at the mathematical expression that defines FM. Phase modulation, or PM, is the other main type of angle modulation. In PM, the phase of the carrier wave is varied according to the instantaneous amplitude of the message signal. While similar to FM, the key difference lies in what aspect of the carrier is changed. PM is often used in digital communication systems and can be converted to FM and vice versa with appropriate circuitry. Both FM and PM share many advantages, including improved signal quality and resistance to noise, but their mathematical treatments and practical implementations differ. Next, let's delve into the mathematical expressions that describe these modulations. Mathematical representation of frequency modulation is crucial for understanding how FM works. In FM, the instantaneous frequency of the carrier is varied by the message signal. The general equation for an FM signal is St AC cos 2 pi plus 2 pi integral m tau d tau, where AC is the carrier amplitude, Fc is the carrier frequency, Kf is the frequency sensitivity, and Mt is the message signal. The integral of the message signal indicates that the frequency deviation depends on the cumulative value of the message. This equation forms the basis for analyzing and designing FM systems. Phase modulation has its own distinct mathematical expression. For PM, the equation is St AC cos 2 pi plus Kp Mt, where Kp is the phase sensitivity and Mt is the message signal. Unlike FM, the phase deviation is directly proportional to the instantaneous value of the message signal, not its integral. This difference leads to unique spectral properties and system behaviors. Understanding these equations helps engineers design modulators and demodulators that efficiently transmit and recover information. Modulation index in FM is a key parameter that determines the extent of frequency deviation relative to the modulating signal. It is defined as the ratio of the frequency deviation to the modulating frequency. A higher modulation index means a wider frequency swing and consequently a broader bandwidth. The modulation index affects both the spectral characteristics and the quality of the transmitted signal. Understanding this concept is essential for optimizing FM systems for different applications, whether it's for narrowband communication or high-fidelity audio broadcasting. Carson's rule provides a practical way to estimate the bandwidth required for an FM signal. According to Carson's rule, the total bandwidth is approximately twice the sum of the maximum frequency deviation and the highest frequency in the modulating signal. This rule helps engineers ensure that FM transmissions fit within allocated frequency bands and avoid interference with adjacent channels. Carson's rule is widely used in both commercial and regulatory settings to plan and manage spectrum usage efficiently. Narrowband FM, or NBFM, is a form of frequency modulation where the frequency deviation is much smaller than the modulating frequency. This results in a signal that occupies a relatively narrow bandwidth, making it suitable for applications like two-way radio and mobile communications. NBFM offers improved noise immunity over amplitude modulation while conserving valuable spectrum space. However, it does not provide the same audio fidelity as wideband FM, making it less suitable for high-quality music broadcasts. Wideband FM, or WBFM, features a much larger frequency deviation compared to narrowband FM. This results in a significantly wider bandwidth, which allows for higher audio fidelity and better noise performance. WBFM is commonly used in FM radio broadcasting where sound quality is a top priority. The trade-off is that WBFM requires more spectrum space, but the benefits in terms of clarity and resistance to interference make it ideal for music and high-quality audio transmissions. Narrowband FM and wideband FM serve different purposes in communication systems. NBFM is ideal for voice communications where bandwidth efficiency is crucial, such as in walkie-talkies and emergency services. WBFM, on the other hand, is preferred for applications demanding high sound quality like commercial FM radio. The choice between NBFM and WBFM depends on the specific requirements of the application, including available spectrum, desired audio quality, and noise environment. Generating FM signals can be accomplished using either direct or indirect methods. Direct methods involve varying the frequency of an oscillator directly in response to the message signal. Indirect methods, on the other hand, use phase modulation techniques to achieve frequency modulation. Both approaches have their own advantages and are chosen based on system requirements, complexity, and performance needs. Let's explore the direct methods first. Voltage-controlled oscillator, or VCO, is a common direct method for generating FM signals. In this approach, the frequency of the oscillator is directly controlled by the input voltage, which is derived from the message signal. As the message signal varies, the output frequency of the VCO changes accordingly, producing an FM signal. VCOs are widely used in both analog and digital communication systems due to their simplicity and effectiveness. Another direct method for FM generation is the reactance modulator. This technique uses a circuit element, such as a capacitor or inductor, whose reactance is varied by the message signal. By changing the reactance, the frequency of the oscillator shifts, resulting in frequency modulation. Reactance modulators are valued for their ability to produce stable FM signals and are often used in radio transmitters. Armstrong method is a classic indirect technique for generating FM signals. It starts by generating a phase-modulated signal, and then converts it into frequency modulation using frequency multipliers and mixers. This method allows for precise control over the frequency deviation and is especially useful in high-quality FM broadcasting. The Armstrong method is more complex than direct methods, but offers greater flexibility and performance. Once an FM signal is transmitted, it must be detected or demodulated at the receiver to recover the original message. FM detection involves converting the frequency variations of the received signal back into amplitude variations that represent the original information. There are several methods for FM detection, each with its own advantages and applications. Let's start by looking at the phase-locked loop, or PLL method. Phase-locked loop, or PLL, is a highly effective method for FM detection. A PLL locks onto the frequency of the incoming FM signal and tracks its variations. The output of the PLL is a voltage that corresponds to the instantaneous frequency of the input, effectively demodulating the FM signal. PLLs are widely used in modern receivers due to their accuracy, stability, and ability to reject noise. Foster-Seeley discriminator is a classic analog circuit used for FM detection. It converts frequency variations in the received signal into amplitude variations, which can then be processed to recover the original message. The Foster-Seeley discriminator is known for its simplicity and effectiveness, especially in analog FM receivers. However, it is more susceptible to amplitude noise compared to PLL-based detectors. Ratio detector is another popular method for FM demodulation. It operates similarly to the Foster-Seeley discriminator, but is designed to be less sensitive to amplitude variations in the received signal. This makes the ratio detector more robust in noisy environments. Ratio detectors are commonly found in FM radio receivers, providing reliable performance for everyday listening. The emphasis is a technique used in FM transmitters to improve the signal-to-noise ratio for higher frequency components of the message signal. By boosting the amplitude of high-frequency signals before transmission, preemphasis helps reduce the impact of noise during transmission. This process is especially important in audio broadcasting, where high-frequency noise can degrade sound quality. At the receiver, a complementary process called de-emphasis is used to restore the original signal balance. De-emphasis is the process applied at the FM receiver to counteract the effects of pre-emphasis applied at the transmitter. It reduces the amplitude of high-frequency components, restoring the original frequency balance of the message signal. This ensures that the audio output is faithful to the original input, with minimized noise and distortion. Pre-emphasis and de-emphasis work together to enhance the overall quality of FM transmission. Frequency modulation is used in a wide range of applications due to its robustness and high-quality transmission capabilities. FM is the standard for commercial radio broadcasting, providing clear and reliable audio to millions of listeners. It's also used in two-way radio communication, television sound transmission, and even in some data communication systems. The versatility and reliability of FM make it a cornerstone of modern wireless communication. FM radio broadcasting is perhaps the most well-known application of frequency modulation. FM's ability to deliver high-fidelity sound with minimal interference has made it the preferred choice for music and talk radio stations worldwide. The wideband nature of FM allows for the transmission of stereo audio and additional data, such as station information and song titles, enhancing the listening experience for audiences everywhere. Two-way radios, such as those used by emergency services, police, and taxi companies, rely on FM for clear and reliable voice communication. The noise immunity of FM ensures that messages are transmitted and received with minimal distortion, even in challenging environments. Narrowband FM is typically used in these applications to conserve spectrum while maintaining communication quality. In analog television systems, FM is used to transmit the audio portion of the broadcast. This ensures that viewers receive clear and consistent sound quality alongside the video signal. FM's resistance to noise and interference is particularly valuable in television broadcasting, where audio clarity is essential for a positive viewing experience. FM is also used in certain data communication systems, particularly where robustness and reliability are required. For example, FM techniques are employed in telemetry, remote control, and some wireless data links. The ability of FM to maintain signal integrity in the presence of noise makes it suitable for these critical applications. Satellite communication systems often use FM for transmitting voice and data signals over long distances. FM's resistance to noise and fatting is particularly beneficial in satellite links, where signals must travel through the atmosphere and space. The reliability of FM ensures that critical information is delivered accurately, even under challenging conditions. Wireless microphones commonly use FM to transmit audio signals from the microphone to the receiver. FM's ability to reject noise and interference ensures that performers and speakers are heard clearly, even in environments with significant electronic noise. This makes FM the technology of choice for live events, broadcasting, and stage performances. Certain medical devices, such as wireless patient monitors, use FM to transmit vital signs and other data to monitoring stations. The reliability and noise immunity of FM are crucial in medical settings, where accurate and timely information can make a significant difference in patient care. Some remote control systems, especially those used for industrial equipment and model vehicles, use FM for reliable command transmission. FM's resistance to interference ensures that control signals are received accurately, reducing the risk of errors and enhancing safety in operation. Marine communication systems, such as those used on ships and boats, often rely on FM for voice and data transmission. The robustness of FM ensures that communication remains clear and reliable, even in harsh marine environments where noise and interference are common. Aviation communication systems use FM for certain types of voice and data links. The clarity and reliability of FM are essential for ensuring safe and effective communication between pilots, air traffic controllers, and ground personnel. FM's noise immunity is particularly valuable in the electrically noisy environment of an aircraft. Industrial automation systems sometimes use FM for wireless control and monitoring of machinery. FM's ability to maintain signal integrity in the presence of electrical noise makes it ideal for factory environments, where reliable communication is essential for safety and efficiency. Amateur radio operators, or hams, frequently use FM for local voice communication. FM's clarity and ease of use make it a popular choice for hobbyists who want to communicate reliably over short to medium distances. Many amateur radio repeaters use FM to extend coverage and improve signal quality. Security systems, including wireless alarms and surveillance equipment, often use FM to transmit signals between sensors and control panels. The reliability and resistance to interference provided by FM help ensure that security alerts are delivered promptly and accurately, enhancing the safety of homes and businesses. Many baby monitors use FM to transmit audio from the baby's room to the parent's receiver. FM's ability to deliver clear sound with minimal interference provides peace of mind for parents, ensuring they can hear their child at all times. Wireless headphones often use FM to transmit audio from the source device to the headphones. FM's resistance to interference ensures high-quality sound, making it a popular choice for personal audio devices, especially in environments with many electronic devices. Garage door openers use FM to transmit signals from the remote control to the door mechanism. FM's reliability and immunity to interference help ensure that the door responds promptly to user commands, providing convenience and security for homeowners. Wireless sensor networks, used in applications like environmental monitoring and smart homes, often use FM for robust data transmission. FM's ability to maintain data integrity in the presence of noise makes it ideal for these distributed systems where reliable communication is essential. Wireless intercom systems use FM to provide clear and reliable communication between different rooms or buildings. FM's noise immunity ensures that conversations remain intelligible, even in environments with significant electronic interference. Wireless doorbells often use FM to transmit the signal from the button to the chime unit. FM's reliability ensures that visitors are always heard, even if the doorbell is located far from the receiver or in a noisy environment. Some wireless keyboards and mice use FM to transmit data between the device and the computer. FM's ability to avoid interference from other wireless devices ensures smooth and responsive operation, making it a popular choice for computer peripherals. Wireless lighting control systems use FM to transmit commands from switches or controllers to light fixtures. FM's reliability and resistance to interference ensure that lighting responds promptly and accurately to user inputs, enhancing convenience and energy efficiency. Wireless alarm systems use FM to transmit signals from sensors to the control panel. FM's robustness ensures that alarms are triggered reliably, providing effective protection for homes and businesses against intrusions and emergencies. Summary: angle modulation, including both frequency and phase modulation, is a cornerstone of modern communication systems. We've explored the fundamental concepts, mathematical expressions, generation and detection methods, and a wide range of applications. FM's robustness, noise immunity, and versatility make it indispensable in fields ranging from broadcasting to industrial automation. Understanding angle modulation equips you with the knowledge to appreciate and work with today's advanced communication technologies. Thank you for joining us on this journey through the world of angle modulation.